Hey, this is Joseph Mills with aria doing our periodic table project. We're going to start off by introducing the SP, D, and F blocks. Here we have our S block, groups 1 and 2. Here's our P block, here's our D block, and here's our F block.
Alright, the reason they're called the S, P, D, or F block is because of the orbitals they have. The S block orbital has a spherical orbital that can hold a maximum of 2 electrons. The P orbital has a dumbbell-shaped orbital that can hold a maximum of 6 electrons. The D block has a double dumbbell-shaped orbital that can hold 10 electrons, and the F block has a F orbital that actually has no definite shape, and it can hold up to 14 electrons.
So these blocks got their name due to their use with electron configuration.
Yes. When writing electron configuration, the S and P blocks, you'll know where they stop. Their final written notation will be in accordance to the period number. The D block will be the period number -1. So if it's a metal in the 5th period, it would actually, when you write it out, it'll be, we'll call it number 6. So it'll have 1, 2, 3, 4. It'll be 4D4, not 5D4 because it's subtracted 1. And the F block will have a subtraction of 2. So if it's at 8 and it's 2 over, it'll be 6F2. Group numbers are named by IUPAC, and they're ordered from 1 through 18, starting from left going all the way to the right.
Now we'll move on to groups and periods on the table. Groups are vertical columns on the periodic table that give us information about their chemical and physical properties. The group number gives the amount of valence electrons with the exception of the transition metals in lanthanides and actinides. So groups, they go across the top in numerical order.
Yes. And the groups also, when they allow us to know the valence electrons, 1 and 2 tell us 1 valence electron and 2. Starting from 13 through 18 will let us know 3, 4, 5, 6, 7, and 8.
It skips the transition metals because their atoms are different. They vary a lot.
Yes. All right. And the periods are horizontal rows on the periodic table. The period number is equal to the principal quantum number, otherwise known as N, to the highest occupied energy level of the elements in the period. So anything on period 1 will determine, it'll say that it has 1 shell, 2 shells, and so on, all the way to 7.
And groups are vertical, periods are horizontal. Now we're into metals, nonmetals, and metalloids, and their location on the periodic table. Metals are located on the left of the periodic table. To the left, they go all the way up to the metalloids. That includes the alkali metals, alkali earth metals, and the transition metals.
Actinides and lanthanides.
Also metals. And once we get to the metalloids, a staircase that runs right here, that tells us the difference between metals and nonmetals because they share properties of both. And on the right side, we have our nonmetals. The physical and chemical properties of metals are that they're good conductors of heat and electricity. They're malleable, which means they're capable of being hammered into thin sheets. They're ductile, capable of being drawn into wires. They have luster, which means they're shiny. They typically lose electrons in chemical reactions. They're oxidized. They have a high density, a high melting point, and they also corrode easily.
Right. Characteristics for nonmetals, both physical and chemical, are that they are poor conductors of heat and electricity. They typically gain electrons in chemical reactions, so otherwise they're known as they reduce. There's no luster, so there's a dull appearance, if any at all. They're brittle, if any of them are solid. They break extremely easily. They're non-ductile, they're non-malleable, they're extremely low density, and they have low melting points.
Okay. Now we're moving into the location of different elements on the periodic table. And we have our alkali metals in group 1. We have our alkali earth metals in group 2. We have our transition metals, which are groups 3 through 12 on the periodic table. And then we have our other metals and other nonmetals. They're not specifically named except for the metalloids. We have our noble gases in group 18 and our halogens in group 17. We also have our lanthanides and actinides down at the bottom, with lanthanides being on top of actinides. They normally would be placed in here, but they can't be due because they wouldn't follow all the rest of the trends in the spacing issue. Okay. Now we're doing vertical and horizontal trends in the periodic table. And first we have the atomic radius, and we know that it increases down a group and it decreases across a period.
The reason why atomic radius increases as you move down the groups is because the shells, you have more shells, more energy levels, so there's more space between the outer shell where the valence electrons are and the nucleus. And the reason why the atomic radius decreases as you move down the period is because the farther you go down the period, there are more valence electrons, which means there's a stronger bond between the nucleus and the electrons, which actually pulls the shells tighter and closer together.
And with ionic radius, we know that it is larger for anions and smaller for cations because in anions there are more electrons, which gives the atom a negative charge. And when you have like charges, we know that they repel, which makes the outer shell larger. And then we have, for cations, that's a positive atom, or has a positive charge. There are more protons in the nucleus. And we know opposites attract, so that shrinks down the atom.
For electron affinity, in general, the values across the period become more negative, with a few exceptions, and they become less negative as they drop down the group. This actually is the same with ionization energy, because that also increases across the period and decreases down the group. And the reason for that is because as you move across, the amount of energy required to pull the valence electron away is increased because there's a stronger connection, there's a stronger bond between the nucleus and the electron. So it is the opposite of the radius. So the tighter the radius, the stronger that the nucleus can hold on to an electron. The larger the radius, the easier it is for a valence electron to be pulled away.
And we know that the atomic radius increases down a group, so as it's farther away from the nucleus, it's easier to pull away.
Yes. And electronegativity decreases down a group and increases across a period. And the reason for that is that as your atomic radius increases, your electronegativity decreases. And so the opposite is true. As your atomic radius decreases, your electronegativity increases.
Now we're going into trends in metallic and non-metallic behavior. We know that metallic character, the trend, is that it increases down a group and it decreases across a period.
Okay. All right. Now we'll be talking about oxidized changing from an oxide to a basic solution, or an amphoteric solution, or an acidic solution. The first one, when a metal oxide reacts with water, they form a metal hydroxide, which generally is going to be a basic solution. For example, potassium oxide reacts with water to produce potassium hydroxide, a very strong basic solution.
And then over here we have our nonmetal oxides. When a nonmetal reacts with water, it forms a nonmetal oxide, and that's an acidic solution. So, for example, carbon dioxide is an acidic gas.
Yes. And the exception to this is silicon dioxide. It does not dissolve in water, but it is classified as an acidic oxide because it can react with sodium hydroxide to form sodium silicate and water.
With our metalloids, we have an aluminum oxide example. It's classified as an amphoteric oxide because, as we know, the metalloids share properties of both metals and nonmetals. And in an amphoteric oxide, it has the ability to act as both an acid and a base. So it shows that it has properties of both metals and nonmetals. We know that it will form an alkaline hydroxide, and this reaction releases hydrogen gas, and it's also exothermic. So the heat generated from the reaction is actually enough to ignite the hydrogen gas into combustion. So we know all these videos on YouTube, the famous videos of just like a hunk of sodium dropped in a big tub of water creates a big explosion.
Yes. And for alkali metals, when they react with halogens, the halogens and the alkali metals will form an ionic alkali metal halide
Salt.
salt.
In halogens with halide ions, we know that a solution of a more reactive halogen will react with a solution of halide ions formed by a less reactive reaction. So you have to have one reaction to be able to lead to another.
Yes.
And for our discussion of the similarities and differences in the properties of elements within the same group, we'll use our alkali metals and halogens as an example. And Mr. Chase, our incredible chem teacher, told us to remember our effing elements, fluorine and francium, as being the most reactive elements. So we know down a group over here, it increases reactivity, and over here, it'll decrease reactivity. So our most reactive halogen is at the top, and our most reactive alkali metal is at the bottom. And you can use these two to determine reactivity within groups on the periodic table. Go.
All right. Now we're going to be talking about the pH changes when compounds such as sodium oxide, magnesium oxide, phosphate, nitrate or sulfate react with water. First, we'll be talking about sodium oxide reacting with water. You're going to get a production of sodium hydroxide, and it's going to be a basic solution, and to balance out the equation we're going to get 2 NaOH to balance out the rest of it, and it's going to be in the presence of water aqueous. It's going to be a basic solution, so it's going to go up in its pH level so that it has a stronger basic level, and sodium hydroxide is actually one of the stronger bases. For magnesium oxide's reaction with water, we're going to get magnesium hydroxide, and there's going to be a 2. Since hydroxide is a polyatomic ion, this 2 is distributed to both of them instead of giving them each 2. For this one, we're also going to get a aqueous solution, and it's also going to be basic because basic solutions are defined as having an OH, and OH determines their basic levels. This is also going to increase in its pH, and it's going to be another basic solution. For the next 3, phosphate reaction with water is going to give us hydrogen, and then PO4 is going to be aqueous, plus hydroxide, which will also be aqueous. So for this one, we're going to get a basic solution. So it's phosphoric acid. It's going to lower its pH level, and it's going to be an acidic solution. We're also going to have an extra hydroxide left to balance out the equation. For nitrate, we're going to get HNO3, and it's going to be plus an extra OH. It's going to be an aqueous solution. Again, since it is just a hydrogen, not a hydroxide, nitric acid is going to be acidic, so its pH is going to decrease. Same thing for
sulfuric acid.
SO4 aqueous, H2 SO4 plus OH. And for the same thing is going to happen. We're going to have a
balanced equation.
We're going to have a balanced equation. Again, our pH is going to decrease, and we're going to have another acidic solution.
And that concludes our periodic table video. I hope you enjoy it.